Okay. Hello, everyone. It's time to start our today's Astroph. Today we have three presenters, Tomoki, Mohan, and Gutu. Who wants to go first? Uh, sorry, Tetsuya-san, can you hear me?
I can hear you. Yes.
Okay. Thank you.
Oh, yes.
I thought that it's a connection problem.
Sure. Sorry. Yes, I can hear you. I don't know
Okay.
one of us.
Thank you. Okay. Who wants to go first? Is
Maybe I can.
Okay. Thank you, Mohan.
Let me share my screen. Okay, can you see my screen?
Yes.
Okay, is it moving?
Yes.
Oh, yes. Okay. Okay, so today I'm going to talk about this paper. So this is published in April this year. So the main goal of this work is to identify the RM rotation measure flare candidates. So actually the rotation measure is uh, people think it can be help to deal discuss about the magneto-ionic environment and provide the important clue in the nature of in their nature. So in their work they use a statistical methods to find the RM flare candidates. So for that they create the model based on the Gaussian fitting, and then they use a 3 sigma threshold. So in their work they identify two candidates with a multiple observational epoch and two candidates in a single epoch. So let's go to the data. So before that I will introduce their framework. So this is their framework for identifying the candidates. So for the data they use both chime and also the fast data of repeating FRBs. So they consider the repeating FRBs that have RM rotation measures, and also they have a clear separation between the burst that have or RM measurements, and also the polarimetric measurements. And then so for the RM measurements, there's a two methods to fit the RM synthesis and RM fitting. So they mostly use QU fitting. They mostly use the QU fitting values, and when it is not available, they use RM synthesis. So here is the table that shows the data that they used. Yes. So and then daily binding. So in the daily binding, they calculate the RM uncertainties using this formula, and then baseline modeling. For the baseline modeling, they use in the step 3 they use the baseline modeling. In the baseline modeling, they use uh, Gaussian Gaussian smoothing with a 20 days range. So why they use Gaussian fitting? Because the RM variation is still unknown in the field of on the FRBs. So they cannot use the they cannot use the parametric one. So that's why they use a statistical method. That's why yes. And then the residual. So the residual significance they use some these formulas to identify the values. So and also they use sometimes when they have RM flare candidates, it can bias the statistical calculations. So they use the initial smoothing value. The threshold is 3 sigma, they mentioned here. So the use of the residual is it can show the peak or the dip, like here I can show the image. What is it? Like this, the dip or the peak, it can show that. Yes, and then if the value is below 3, it is rejected, and then above 3 is taken to the another epoch. So the results, so when it comes to the results, so they show the uh, false positive rate for the threshold that they choose is 0.13 percentage on 3 per source. So they argue that this is a significantly acceptable range of threshold, and then their candidate ranges here. So this FRB, this particular FRB, they say as a very good RM flare candidate. For example, if you see here, um, what is the FRB name? 2020529. Okay, so if you see here, the SNR value is all above the threshold that they fix. So compared to other FRBs, and if you say the MJD, so the mid value is present here in these particular FRBs, and then they say these two FRBs are having the only one player, sorry, only one. For example, if you see in this image, so they don't have continuous peak for unlike this FRB. So they have only the RM flare only in two particular MJD values, and this is what they say as a single epoch MJD, and in the abstract they say as two kind of the two additional single epoch candidates and multiple epoch candidates. So this is what the single epoch candidates, like the shown here. And then, so when it comes to the conclusion, so um, I'm not sure about the conclusion. So they say uh, their method rejects the outliers and identify the RM player candidates, and so this RM, if the RM is a RM player's candidate is confirmed, then it suggests the magnetized environment in the line of sight, and the amplitude of the candidate range is 10 to 600, this range in one sigma duration, in the range from 0.5 to 20 days. Yes, that's it.
Okay, thank you, Mohan. Is there any questions or comments to Mohan? If no, we can move on to next presenter, who is. Uh, thank you, Goto.
Okay, I'm going to present the aging accretion and the black hole growth across compact and extended galaxy evolution phases. Through in these studies, they investigate the link between galaxy compactness and the black hole growth at the redshift between 0.5 to 3 0.53 in both compact and extended phase. Finally, or they get agent fraction increases with compactness in star-forming galaxies and decrease in quiescent galaxies with both the compact and the extended subpopulation, which demonstrating that agent activity depends closely on the structural properties of galaxies. In these studies, they try to differentiate their population into compact, based on compactness of the galaxies, as well as based on the star forming and quiescent galaxies to explore the relationship between the relationship between compactness and active galactic nuclei activities. That is what they studied in their paper. As we know, the evolution of galaxies appears closely linked with the growth of supermassive black hole, and the higher galaxy star formation rates are associated with increased agent activity. That means as agent activities increase, it must probably have higher galaxy star formation rate. When it comes to the data they used, the selection of their parent sample, or they used to they used data from two catalog, the Deep Hubble Space Telescope imaging of the 5 candle survey fields and the Chandra X-ray imaging used to identify alien galaxies. They used specifically they incorporate Chandra X-ray imaging to which has a deep image to differentiate or decompose the agent properties from the agent activities in a clear way. The other thing is they has considered a redshift between 0.5 to 3. When it comes to the meteorology part, in the meteorology part, there are 3 physical quantities or main physical quantities: stellar mass and star formation rate, which is calculated from the spectral energy distribution by using the fast code to fit the CD models. These models or this fast code is the new version fast code is used to allow them to include the agent component in the CD4 galaxies. Here they calculate the density or the central surface mass density within 1 kilo parts by using this formula or by taking stellar mass from the CD calculation and I times 1 kilopascal square. So by using this formula, they calculated or they got the density of the central surface mass density. And here we have 3 things: density, surface mass density, star formation rate, and stellar mass. They estimated this physical quantities. Based on that, they had into the different bins spanning the range of 0.5 to 3 to control or to handle their data properly. That is all about the way they try to they has done they have handled their data, but specifically I want to focus on this. Yeah, this figure. Finally, this figure shows the relationship, or they are showed the fractional contribution number corresponds to the calculated density. In this case, the above one or the top figures shows the lower redshift 0.5 to 1.4 based on different limits. By control the luminosity and the luminosity stellar mass ratio and the luminosity to density. They try to see they try to investigate the relationship between the eigenfraction as the function of density. Based on that, as the compactness increases, as the compactness of the galaxies increases, the eigenfraction also increases. So this is the main figure they show to explore the to investigate the relationship between the density and the eigenfractions. Finally, they conclude or finally, AGN activities enhanced during the compact star formation phase with 10 to 25% of compact star forming galaxies found to host an AGN. And in addition, while they may have enhanced activating rate, they have a broad range of accretion rate that are not substantially enhanced compared to the extended star formation population. As generally, they investigated the compacted the eigenfraction or eigenactivity corresponds to the density or the mass surface mass density. That is what they addressed in their paper as well as summarized, concluding that with these findings. But in this paper, I forgot to mention they use the probability distribution to include all their AGNs in their analysis, because when we cut AGN fraction or consider only loud AGN galaxies, we may end up with a small number of AGNs. To solve this problem or to tackle this one, they used probability distribution. Then they include all galaxies or all samples, which is very important to robust their statistical. That is all about this pair. If you have any question. Okay.
Oh, good job. Thank you. I have a question about figure 10.
Okay.
I just got confused. So they are saying this is AGN fraction in y-axis?
Yeah. But
But then
sorry.
they have three different panels.
Yeah.
So the difference in these three different definition of agents, how come this, I want to understand this figure.
Okay. For the right figures, the right-hand figures, they control their samples based on this criteria, or luminosity should be greater than 42, log of 42.
You mean left, right?
Yeah.
Not right.
The right. Okay.
So this X-ray luminosity is higher than, say, 10 to the 42. Is this a definition of AGN?
Yeah, that limit is to incorporate all agents as much as possible. That is why they take greater than 42. Yeah.
So they think that if X-ray luminosity is higher than this value, they are all agents.
Yeah, they are not, they all are not agent, but they use one trick. If even if they are not agent, but they included in their analysis by using the probability distribution to weight each of galaxies as their contribution.
I really don't understand this. So are they using all the agent samples to plot this figure? Or y-axis is the definition? I mean, this.
Okay.
I think how do they find agent?
To analyze this one, firstly, they use agent, those galaxies, those has greater than 42 luminosity,
Oh,
but those galaxies may not be detected as agents,
oh, I see, I see, I see.
but
So
their agent fraction is calculated as based on their contribution. For example, if we include only agents, we need to discard the some the some amount of agent number, right? But they included, then they wait for their contribution.
oh, so that's difficult. So so that means y-axis is actually, is this really agent fraction?
Not all these galaxies are agent.
I don't, but why this caption is saying it's agent fraction?
Yeah. The y-axis is agent fraction, right?
Am I agent?
Sorry.
Yeah.
I mean, y-axis shows agent fractions, and the x-axis shows the density.
Ah, really? Okay. But then, let's say y-axis is agent fraction, but
Yeah.
then they have different indicators. Actually, they have 3 panels here.
Yeah.
So they use different indicators to express agent fraction.
Yeah.
Ah,
Yeah.
okay.
They cut their samples. For example, when we consider the right hand side figure, they cut their samples. Though they used the galaxies, those have greater than 42 luminosity.
Among that sample, you count how many agents are there, then calculate fraction.
Yeah, that is what they did. For the middle one, they take luminosity to stellar mass ratio as the B.
Oh, I see. Oh, I see. Thank you. Now I think I understand. Just for my information, how do they define AGNs in this study? How do they differentiate between AGNs and galaxies? In this, I think there are multiple ways, right?
Yeah, there.
Classify.
Let me check. I forget. Sorry. Sorry, I forget where I see it.
Oh, I see. Yeah. Okay.
But they didn't differentiate to agent and non-agent, or detect agent and non-detect agent. They differentiate only based on the compactness and the coefficient and the star formation. Based on that, they used all galaxies to calculate or to show the relation of agent fraction with compactness. But in our figure 10, they consider only, for example, right-hand side. On the right-hand side, they consider only galaxies those have greater than 42 luminosity. For the middle one, they consider the stellar mass to luminosity to stellar mass ratio, the greater than 32. That is the way they did, not differentiate into agent and non-agent. Because if they differentiate that one, they end up with a small number of agents. So to solve that one, they use all sample data instead of differentiate them, then calculate for each bin the mean value of agent fraction across the compactness or the density.
Thank you very much.
Okay, thank you.
Tatsuya-san, I think in figure 4 they have mentioned about the star formation rate versus the star formation rate of the main sequence. And in the SED fitting one, they consider about the AGN and galaxy contribution. I think that's how they classify AGN and non-AGNs. In figure 4, yeah. This is what I got from this. Because they show like galaxy only and galaxy plus AGN data points.
Galaxy plus. Yes, but then they are just overplotted, right? Say, I wonder how they differentiate.
Yeah, I don't really understand how they have selected the fraction, but I mean, from this paper, what this figure shows is, I guess, like if they in the SED fitting when they can't like have an agent component, or if they don't have an agent component, and if the agent like after including the agent component, if maybe the fitting is better, they say that that's an agent plus the galaxy, I think. Yeah. Also, I have one, yes. Thanks. Also, I have one more question, Gutu. So I don't understand from figure 10. They are saying that the agent fraction basically increases with the more compact, more active the agent would be. From figure 10, it says that it will be more energetic or more active if it is compact, right? But only in the case of star-forming galaxies.
Yeah.
Which makes sense if you have more star-forming regions and if you could fuel it to the central black hole, then of course it will be more luminous. But why in the case of quiescent galaxies, they have the reverse trend? I mean, it should be even more prominent for the quiescent galaxy, right? That it shows the reverse trend where when the galaxies is compact, the luminosity decreases or the agent fraction decreases. So,
Yeah, I understand your question, but
okay, then maybe later.
Okay, thank you, Gutu. Is there any quick questions or comments to Gutu? If no, we can move on to Tomoki.
Okay.
Thank you.
Can you see my screen?
Yes.
Okay. Today, I would like to introduce this paper. In this paper, the authors try to measure Hubble constant using dispersion measure distribution of unlocalized FRBs. And one interesting point of this paper is they only focus on dispersion measure distribution of FRBs. and assuming theoretical models, they can estimate, and assuming theoretical models, and combine that theoretical model and observed FRB dispersion measure distribution, they measured Hubble constant. And this value is what they obtained from this their calculations. Yeah, okay. Let me briefly introduce what they're doing. I think this one, okay. This paper may be submitted to PRL, and from CHIME second catalog, they pick up 2,000 unlocalized FRBs following some criteria, and using this data, they estimate Hubble constant. And what here they describe their model. They decompose DM to Milky Way component and extragalactic component, and they evaluate probability distribution function of DMEXT for given parameters. Yeah, I skipped details. Okay. Yeah, this is the observed observed dispersion measure PDF for given parameter set, and it contains some components. One is PDF of extragalactic. This is a PDF for DM extragalactic component, and this is the event FRB distribution in redshift, and this is detection probability, and this is I forgot, sorry, something, but they call this the instrumental selection function of the DM observed, this value. And they model this part shown as here, and this part is modeled by this kind of simple distribution functions, and the rate is so proportional to star formation rate to the power of n. This is parameter. And for detection and DM instrumental parts, they follow a CHIME first catalog. They used value obtained in CHIME first catalog. Something like this or this kind of things. And energy distribution of FRBs, they assume this kind of power distributions. And by combining these all models, they can we can obtain PDF of observed dispersion measure. And comparing this PDF and observed DM, they estimate Hubble constant. This is what they did. And this is estimated Hubble parameters. They tried to case one is fixed cutoff energy here, and the other is free. The other is not fixed cutoff energies, and resulted something like this. And yeah, this is the corner plot of the estimated parameters. And this is Hubble constant. And from this panel, we can understand that Hubble constant is strongly correlated with cutoff energies, and maybe weakly correlated with event rate, and independent of DM halo or power law spectrum, or sigma host. And I'm not sure why, but in their calculation, they conclude that Hubble parameter is not correlated with DM host. This is opposite from our distinctions, but in their model, they conclude that H0 and mu host is not correlated, and something like this. And so estimates the DM host, and this is a bit small value, I think, because mu host is defined here. And so the estimated DM host is e to the power of about 3 or 4. And this is not so high, I think. And this is their result. Anyway, the interesting point of this paper is they only used DM distributions and estimate these parameters. Okay, that's all from this paper. Thank you very much.
Okay, thank you, Tomoki. Is there any question or comment, Tomoki?
Maybe my question say, what is their final value of Hubble constant?
This value.
Okay, so this is actually more than 10%.
Yeah.
I was wondering, so they say this Hubble constant doesn't depend on DM host, but actually this dependency is, accommodated in this error bar. I mean, this range is, but wait.
But
we should have correlation here.
Yeah, in something like maybe this.
Yeah.
I cannot see that point of trend in this figure.
I see.
I don't know why.
I see. So, but then this is saying rather this E star has more correlation?
Yes. Because E star changes how far FRBs we can observe.
Yeah.
And it can affect the DM distribution because DM cosmic depend on this value.
Yeah, I see. So in this sense, actually, without redshift information, so it's hard to derive the value. Say, even using this 2000, they are using CHAM2 catalog, right?
Yes. 2000 FRBs.
2000 FRBs. Okay. Then, yeah, I just wonder, maybe it's better to have redshift information.
Yes, I think so.
Even though number sample may be small, but then this is more than 10%. So this is, I think John Chin's paper is actually better than this in terms of error bar. It's difficult to compare directly, but
I think the bad point of this paper is they include both uncertainty of FRBs and cosmologies.
Oh, right. These two things affect, right?
Yeah.
So, yeah. A good thing is they can use many samples.
Yes.
But then this large number doesn't help to reduce the error bar.
Maybe. Sorry, they may mention something like this. Yeah, FRB energy distribution may help us reduce.
Because they say it correlates, right?
Yes.
Okay. I see.
Yeah.
It's good to know.
Okay.
Okay, thank you.
Thank you very much.
Is there any other questions or comments to Tomoki? If no, thank you. And for tomorrow, we need 3 volunteers. Okay, thank you, Priyanka. Thank you, Betty. And one more volunteer. Thank you, Tetsuya-san. Okay, If there is no other specific questions or comments, we can close the meeting. And thank you all.
Sorry. I'm sorry. I had a meeting tomorrow. I'm sorry. I cannot do that. I'm so sorry.
Oh, okay.
Sorry.
No
Sorry.
problem. Okay. Any other volunteers? One person. Okay. How about Dora?
Is Zora okay?
No.
No.
Yes. Shatari, can you hear me? Okay. Can you introduce yourself? Okay, okay. Okay, so so for tomorrow we have Shataro, Betty, and Priyanka. Thank you so much.
Thank you so much.
Thank you and goodbye.
Thank you. Bye bye.
Bye bye.